Proposition 11 says to draw a straight line at right angles to a given straight line from a given point. Okay, so let AB be the given straight line and C the point. So we have to draw a line from the point C, which is at right angles to the straight line AB. Let D be taken at random on AC. You might say, well, why can't it just be A or C? In that case, the triangles we're going to invoke in a moment would be degenerate. So it's sort of implicit that it shouldn't be the endpoints. Could be the midpoint. I guess we don't actually have a means of constructing the midpoint yet, which is maybe why this slightly odd formulation with random points is being used. Because I suppose what we could do is something like you're given C. You could take the line segment BC and construct a segment in AC of that length and pick the one that's smaller so that it's not, I mean, you could name a point on either AC or BC by, if C is not the midpoint, using that trick, I guess. But we'll just continue with this random business for now.
Does Euclid use the word random?
Yeah, he does. Yeah. Oh, well, okay, the translation does. I haven't looked at the original Greek to see, but presumably it does, yeah.
Because I wonder, like, I know there's some, like, history on what people thought, like, random means. And I wonder if there was a sort of specific, like, interpretation of random at the time.
Yeah, that's an interesting question. Okay, so hopefully it's kind of reasonably close to being the same length. Proposition 1.3 allows us to, given a point in a line segment, construct a line. Maybe I should indicate. So Proposition 1.3 says we can take C and we can draw a line of the same length as CD on the segment CB. It's kind of a bit of overkill because we just do that by drawing a circle. So, I mean, we could just... invoking Proposition 1.3 is a little tricky because, you know, nothing stops that line segment somehow from sticking out the other side. Or at least you'd have to worry about that. But take a circle of radius CD at C, and then that intersects at E. So that's what effectively we're using from Proposition 1.3. Alright, now on DE, construct the equilateral triangle FDE. And so I guess that's Proposition 1. I should be making use of these alternative pens. Okay, let FC be joined. So obviously we claim that this is a right angle. So we claim FC is at right angles to AB. And a common notion defines that by saying that the angle FCB is equal to the angle FCA. So that's what we have to show. For since DC is equal to CE by construction, and CF is common, and we know the other sides of those two triangles are equal, namely FD is equal to FE, because that was an equilateral triangle, it follows from proposition 1.8 that the angle DCF is equal to the angle ECF. Oh, but that's what we had to show. Okay, so we can construct a straight line at right angles to any given straight line from a given point. Any questions about that one? Okay, you want to do the next one, Kenneth?
Cool, thanks, Dan. So the next one is quite similar to this one as we were talking about before. I'll leave this one up. I'll go to the next board. So proposition 12. Oh, I'm on blue. So you guys made some updates to the boards. This looks pretty cool.
Yeah, you might also find it useful to, if you look at the very left of the toolbar, you can have two different pens. So I have one set up with green and one set up with white, or any other variation you want.
So nice. So you can switch quickly without having to choose colors. Nice. Cool. Fantastic. Thanks, Dan. So the previous proposition was about constructing a perpendicular from a point on a line. So this one is about dropping a perpendicular from a point off the line. Very similar, and I suppose the proof is also similar as well. I'll start with the proposition or the construction. So you want to construct a line through a point perpendicular to a given line. Oh, off the board there. How do I guess the eraser is, yeah, there you go. Yeah. To a given line. So just to emphasize that this point here is off the line, right? So we'll start with the point here, which is going to be C. Oh, hang on. Which is going to be, we're going to call C. The line here that we've got, we'll call AB. And so we're going to construct a few things to help us prove prove that the construction, well, we're going to define the construction and then prove that the construction actually gives us what we want. So the construction is that we choose a point D on the other side of AB. So when I was reading this, I thought it was strange how they were talking about choosing a point on the other side of AB. Why not just choose a point on AB? But then I realized that if you choose a point on AB and it happens to be the point where you drop the perpendicular from C and that's is perpendicular to AB at that point, none of the constructions in this proposition works. So we're going to choose the point on the other side, right? I'll use blue. Actually, make it so that it's not super fat, right? So we're going to choose point D. I'm going to draw a circle. Draw a circle with radius CD and center C, right? So this circle is not going to reach all the way. I'm trying to draw this without destroying the text. Oh, all right. Or maybe it's okay. Is there a circle? And this circle is going to hit the line AB at G and H, E. And we're going to form this triangle, GCE, right? And we're going to use the fact that we can bisect a line segment to get this point H, all right? So we're going to find this point H, which bisects the line segment GE, all right? I'm just going to draw the line from CH, not the best drawing in the world. These are the same. The claim is that this is a right angle. Okay, so going back to here, I guess I'll just very quickly write down the construction instead of just drawing it. So construct circle centered at C with radius CD, right? And let G and E be the points. E be points on AB where the circle intersects AB, right? And let H be the midpoint of GE. And I don't remember the proposition. Dan, do you remember which proposition allows us to cut, to bisect GE?
Yeah, it was proposition 10. I forgot about that 10 minutes ago. In doing proposition 11, I could have made use of that to avoid using the random formulation.
Oh, right, yeah. So, okay, so you know proposition 10, right?
Yeah.
So that's how it goes. And the proof of this is again using congruent triangles. So I guess we're going to use proposition. I'm going to be consistent here, and like what you were doing, use propositions in blue, maybe proposition 8, right? And so we're basically going to say that the angle CHG is equal to CHE. This is actually, well, angle CHG. Oh, wait, hang on, sorry. We're going to show that angles CHG and CHE the same. If they're the same, then they're right angles. And what we're actually going to do is we're going to use proposition 8, and we're going to, use a congruent triangle. So CG, right, is equal to CE, right, because they're both radii of the same circle. And we also have GH is equal to HE by construction, right? Midpoint, it's a midpoint. And we have a common side, which is CH, which is a common side. And so proposition 8 tells us that these two triangles are the same. So the implication is that the triangle CHG, the triangle here, is congruent or exactly the same as the triangle CHE. And in particular, the angle CHG is equal to the angle CHE. Right. So since I'm out of the room, I'll just kind of say that's it. Like, since they're both the same angles, definition 1.10 tells us that they must be both right angles because they lie on a line. So maybe I'll just leave it as something that I'll just say. Yeah, you will use definition 1.10 to conclude that this is a right angle. Cool. So so that's it.
Just quickly, there seems to be some value in, I mean, not to criticize the drawing, but like inaccurate drawings of like it seems somewhat valuable for the line to not look like a right angle yet when you draw it, because like it like because some of these proofs are sort of hard to it's hard to see what it's more just obvious that it's true because you can look at it and see, oh, it's a right angle. But if it's like drawn to sort of be a bit warped, then you have to sort of look at all the constraints and convince yourself that it like forces it to be adjusted into a right angle or something.
Yeah, that's totally warped. I know. My picture's not the best.
But I think Euclid, some of these diagrams definitely emphasize that as a means of kind of not making it too self-evident. Yeah, it's interesting. I read a couple of articles about the role of diagrams in Euclid, and there's some interesting comments on exactly this point. Maybe I'll post them in the Discord later.
Cool, thanks.
Okay, so proposition 13, it's more or less just an examination of common notions 1 and 2, which I'll remind you of in a second. Let me state it first, though. So if a straight line is set up on if a straight line set up on a straight line makes angles. Maybe it's better to draw the picture. Talking about imperfect diagrams, this is a straight line despite appearances. So there's DC, and here's BA. Okay, so that's one straight line, AB, set up on another straight line, DC, and the two angles being CBA and ABD. It will make either two right angles or angles equal to two right angles.
Sorry to interrupt.
Yeah.
But actually one of the, folders got stuck in another folder. Not move it out.
I'll come help you a bit later, okay? I'm in the middle of something right now. Okay, so well, if the two angles are equal, then there is nothing to prove. And if not, let BE be drawn at right angles to DC. So this is using proposition 11. Here's BE. Okay. Therefore, CBE and EBD are two right angles. Okay, so now we make use of, so common notion 1 says that equality is transitive. So if A is equal to B and B is equal to C, then A is equal to C. And common notion 2 in modern language says that addition is compatible with the equivalence relation of equality. So if you add equal things to equal things, the wholes are equal. That's, I think, literally what common notion 2 says. Okay, so we're going to make use of that. I'll just write down the equations. Obviously, Euclid writes it out in words. Okay, since the angle CBE is equal to the two angles CBA and ABE, right, so CBE is equal to CBA plus EBA. Adding EBD to each, they remain equal, the left and right hand side. So this is by what I was just saying. So this is common notion 2. Okay, so let's call that star, I guess. Now, since the angle DBA is equal to the two angles DBE and EBA, so since DBA is equal to DBE plus EBA, adding ABC to each, maybe I've got the ordering of the letters a bit around the other way, but this is again by common notion 2. But the angles CBE, EBD were proved equal to the same three angles, right? So let's have a look. So EBA, EBA, ABC, ABC, EBD, DBE. Okay, so the right-hand sides there are equal. So by common notion 1, which is transitivity of equality, we have that EBD plus CBE is equal to ABC plus DBA. But what were we trying to show? Well, we were trying to show that if we set up this straight line here, it will either make two right angles, we dispense with that case, or angles equal to two right angles. That is, we were trying to prove that the sum of those two was equal to two right angles. But that's exactly what we've done, I hope. Right, so ABC plus DBA is equal to the sum of two right angles, which is this part here underlined in green. Okay, so that's it. Any questions?
Cool, thanks, Dan.
Yeah. All right, I think we made it just in time, right?